Today I present representing bending for large language model safety. Modern LLMs are instruction tuned to be helpful and safe. They answer benign requests correctly and refuse clearly harmful ones. However, the safety risks under adversarial manipulations. Jailbreaks still work. With carefully designed prompts, model can be coerced into producing harmful outputs. These attacks bypass standard safety training, revealing a gap between alignment and robustness. Methods like RLHP and DPO mainly constrain the output behavior, but adversarial prompts can bypass these constraints. Output level alignment does not generalize well to OOD attacks. So why existing fixes fall short? Unlearning and activation steering reduce harmful behavior, but for activation steering, output-focused methods struggles under white box attacks. Inference time steering adds complexity and then hurts general reasoning ability. So embed safety in the represent space came to topic. Reason work suggests safety should be enforced inside the model's internal representation. Circuit breaker, for example, disrupts harmful representation pathways. This motivates a representation level approach to safety. Paper's core idea is bending representation for safety. In unsafe queries, original model drifts toward harmful regions. Paper's idea is simple. Preserve safe representations and bend unsafe ones away from harmful regions. For paper's contribution, this paper introduced LabBand, a train time safety method that bans internal representations using activation difference. Paper achieves up to 95% ASL reduction across diverse black box and white box jailbreak benchmarks and outperforms prior methods such as circuit breaker, RMU, and MPU. Paper preserves usability and general capability while ensuring safety as well. So here's the brief introduction of how representation bending works. For safe prompts and safe responses, we compare representation from the original model and then minus one another to get a difference vector Vs, which should be the safe representation difference vector. This preserves normal behavior and usability. For the unsafe case, like unsafe prompt but safe response, also with unsafe prompt, and the model also answered unsafe response. The paper get a representation for both cases and then minus one another to get unsafe representation difference vector. Then also, the paper gathered the representation of all cases with unsafe prompt to gather model's reaction for the unsafe prompt, which should be unsafe representation set. So this is how it works. They make left band from LoRa fine-tuning the original model. LoRa fine-tuning loss function is like this. So they apply the big L2 norm for unsafe representation difference vector VU. And then they apply small L2 norm to safe representation difference vector VS. So they can adjust the model to increase the safe response and decrease on the unsafe response. And then a set of accumulated representation from unsafe prompts, which is written by AU, is used to collapse unsafe behavior into a stable diffuser direction with using cosine similarity. So these are the results. When seeing the results for two different models, when we applied red band and then other LLM safety methods, we can see the paper's red band actually scored higher attack success rates than other methods, both for black box jailbox and white box jailbox as also. The paper also shows while the method was able to ensure the safety among the most previous methods, it was also able to maintain the model's basic capability scores. So this is the result on model being trained for general task. And then we can see the overall score. We can confirm that model hasn't lost its general capability ability. So this is the end of my presentation. Thank you very much.